Hi, I'm Tommy, and this will be my Deque project presentation. So first, let's go over the three implementations. For ArrayDeque, all we really had to implement was a bug fix with the increment method not being called correctly. Although it was just a problem with one line of code, it did take a while to find, and I had to basically run the code line by line and visualize what was happening in memory to locate the bug. But in the end, finding out what was causing the issue was pretty satisfying. Um, so for ArrayListDeque, I guess what I was proud of for this class was just how simply methods like add last could be done, because you could just give all the work to the ArrayList class. So something like this method could just be written in one line. Next, we have LinkedDeque. For this class, the linked nature of this implementation really made it convenient to add or subtract or remove from both the front and the back, because once you have the Sentinel nodes, you didn't really need any loops. All you had to do is all you had to do in inserting an element is just rearrange the nodes, the fields, the next and previous fields. So that was pretty convenient. So next, let's go over the asymptotic analysis for ArrayDeque and ArrayListDeque for these four methods. In the worst case, we have two things that could happen, assuming that size is not 0, because if size is equal to 0, then the remove methods will not work as properly. So in case 1, we have the possibility in which the deck is either too full or too empty, in which case you will need to resize. So actually, in the worst case, that's always a possibility. And because resize requires copying every element into a new deck or a new array or array list, it's going to make our runtime at least theta of n for all of these methods. As it turns out, there wasn't any nested loops, so because of case 1, there wasn't any nested loops in all of these methods, so because of case 1's possibility, we do have theta of n for all of ArrayDeque's method. For ArrayListDeque's methods, although it's also all O of n for the add first and remove first methods, they actually work a little bit differently, because you actually, in the worst case, you have to deal with both case 1 and case 2, where because of how ArrayList adds an element, you are really when you add an element to the first index, you're really making a new array by shifting everything over, or shifting everything to its previous spot in the case of removing an element from the first spot. So you would really be running, in the worst case, you would be resizing and then shifting everything over, which would be 2 for loops. But although that would also give you a theta of n runtime, that would be arguably a worse theta of n than the ArrayDeque's counterparts. In the best case, obviously we have the case where resize is unnecessary, and due to that possibility, due to the fact that we're ruling out resizing, we see that ArrayDeque's method all would run in theta of n. And because this is the best case, something else that could technically happen is that size is equal to 0. And because in that case, the remove methods would execute in one line, that would also be a constant runtime, or theta of n. Theta of 1. And interestingly, for ArrayListDeque's add first method, there is no constant runtime, because it turns out that you're always going to be shifting elements over when you are working with an array list, working with the first element of an array list. And for ArrayListDeque's remove first, we do have that possibility where size is equal to 0, but in any other case where the method is actually working properly, just like at first, you wouldn't have a constant runtime. So here is the experimental runtime for the three classes: ArrayDeque, ArrayListDeque, and LinkDeque. So seeing that all of those graphs were linear, I decided to summarize the results just based on comparing their slopes. And in this experimental analysis, by the way, we're dealing with two different methods, two different types of methods actually, because here at last isn't called once, but it's called n times, so that I know we found before that at last runs in constant time, but when you are calling it n times, and each call takes a constant amount of time, it would make sense that running at last n times would be linear with respect to n. And that is for ArrayDeque and ArrayListDeque. And for LinkDeque, because we know that at last is also linear because you're simply rearranging the pointers in the nodes, it does make sense that that would also have a pretty much constant slope too. So we see that calling at last n times is these three classes are giving us a very small slope, but ArrayListDeque's at last does perform a bit better than ArrayDeque and LinkDeque. It does also make sense that both ArrayDeque and ArrayListDeque's get method would still run in constant time because it's only being called once in this test here to retrieve the middle element. So that will just require, so it makes sense that it wouldn't depend. It would always take the same amount of time, no matter what the size of the array is. However, LinkDeque's get middle operation, it would require actually looping to the middle element, which would cause it to run in constant time, and as you see here, to have a non-zero slope. So seeing that result, someone might conclude that, hey, isn't ArrayListDeque actually better at adding to the last element? But it turns out that that is actually a very limited. It doesn't really paint the full picture because, as we see here, if we test a method that actually such as at first, where, as we talked about before, ArrayListDeque actually doesn't even have a constant run. Even in the best case, ArrayListDeque doesn't even have a constant runtime. When ran n times, we see a clear difference in their growth rate, and it's clear that ArrayDeque is better